Welcome to Two Projects. In this video, we are going to explain the project, a holistic approach on airfare price prediction using machine learning techniques. Introduction. The project focuses on analyzing and predicting airfare prices for different airline companies and destinations. The primary objective is to understand the pricing policies among various airlines and provide a comprehensive approach to the airfare prediction problem. In the dynamic and globalized market of airline travel, understanding and predicting airfare prices play a crucial role for both consumers and industry professionals. The project addresses the increasing demand for more sophisticated algorithms and software, specifically leveraging machine learning techniques to optimize dynamic pricing strategies. This is essential for adapting to market changes quickly and efficiently. And the project employs advanced machine learning techniques including machine learning with 8 state-of-the-art models, deep learning with 6 convolutional neural network models, and quantum machine learning, that is QML, with 2 models. These techniques are applied to a dataset comprising 136,917 flight records from prominent airline companies including Aegean, Turkish, Austrian, and Lufthansa Airlines. Travelers and consumers benefit by gaining insights into the pricing policies of different airlines, allowing them to make more informed and cost-effective decisions when booking flights. Industry professionals can use the findings to optimize their pricing strategies, understand competition dynamics, and enhance their overall competitiveness in the global market. And the project contributes to the research community by exploring the application of quantum machine learning in the context of airfare prices prediction, offering insights into its performance compared to classical machine learning and deep learning models. Objective of the project. So the first objective is to create a robust analysis framework that considers various factors influencing airfare prices. This involves a detailed examination of pricing dynamics specific to different airline companies and destinations. The goal is to develop a holistic understanding of the variables that impact ticket costs. Leveraging cutting-edge machine learning techniques such as machine learning, deep learning, and quantum machine learning, the project aims to predict and comprehend the pricing policies employed by airlines. This objective involves applying state-of-the-art algorithms to analyze a substantial dataset of flight records and extract patterns related to pricing strategies. The project aims to provide valuable insights for end users, primarily travelers. By analyzing and interpreting the pricing policies of different airline companies, the objective is to empower travelers with information that facilitates informed decision making. This includes identifying cost-effective travel choices based on the observed patterns in airfare pricing. And the final objective is to contribute to the research community by exploring and advancing the application of quantum machine learning in the context of airfare prediction. This entails comparing the performance of QML models with classical machine learning and deep learning models. The goal is to enhance understanding and potentially uncover new possibilities at the intersection of quantum computing and airfare price dynamics. Requirements needed to execute this project are software requirements. Software used is Anaconda, primary language used is Python, front-end framework used is Flask, backend framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Now we'll discuss the working modules of flow of work. The first step is importing required packages. In this step, we import necessary Python libraries and framework that will be used throughout the project. This includes packages for data manipulation such as pandas, machine learning like sklearn, deep learning such as TensorFlow or PyTorch, data visualization like Matplotlib and Seaborn. The second step is exploring the dataset. In this step, 2 experiments are conducted to gain insights into airfare records from major airlines. The first experiment involves a detailed examination of flight records for Aegean, Austrian, Lufthansa, and Turkish Airlines on specific routes originated from Thessaloniki. These routes include destinations like Amsterdam, Stockholm, Brussels, Paris, Lisbon, and Vienna. The second experiment takes a holistic approach, exploring the dataset collectively for all airlines without distinguishing specific routes. These explorations aim to uncover patterns, variations, and factors influencing airfare prices for informed feature selection and subsequent model development. The third step is data processing. This step focuses on cleaning and preparing the dataset for analysis. Tasks include handling missing values, removing duplicate data, and addressing any inconsistencies or outliers. The next step is visualization using Seaborn and Matplotlib. In this step, we employ Seaborn and Matplotlib to create visual charts and graphs, facilitating a better understanding of dataset characteristics. The next step is feature extraction. So feature extraction involves selecting relevant information from the dataset. In this step, we are dropping a time-based column due to format issues. Feature extraction is crucial for creating a concise and meaningful set of features that can be used for model training. The next step is feature selection. This step involves choosing the most important features that will contribute to the model's performance. Various techniques such as correlation analysis of feature importance from tree-based models are applied to select the most relevant features. The next step is appending selected features to X and target column to Y. Here we organize the data into input features for X and the target variable to Y. X contains the selected features while Y contains the variable we want to predict, which in this case is airfare prices. The next step is splitting the data to train and test. Here the dataset is divided into training and testing subsets. The training subset is used to train the machine learning models, while the testing subset is reserved for evaluating the model's performance on unseen data. And the next step is training and building the model. This involves selecting and training machine learning models using the training data. We use a diverse set of models including ADA boost, bagging, gradient boosting, decision tree, random forest, extra tree, support vector regression, multiple layer perceptron, and various deep learning models like VGG11, VGG13, ResNet18, etc. And a user-friendly Flask-based frontend with authentication was developed. And the next step is Flask framework with SQLite for sign-up and sign-in. In this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. And in the next step, after signing in, users provide input through the front-end interface. The input data is pre-processed to prepare them for prediction by the trained models. This pre-processing step ensures that user-provided data are in a suitable format for the model. And the pre-processed input is fed into the trained models for prediction. The best performing model is selected to make predictions based on the input data. And the predicted outcome is displayed through the front-end interface, allowing the user to view the results of the model's predictions or analysis. Now we'll understand about the algorithms used. So we have done 2 experiments in this project. In the first experiment, we studied how specific airlines Aegean, Austrian, Lufthansa, Turkish affect airfare prices on different routes. And in the second experiment, we grouped airlines into types, budget or premium, to explore their impact on overall airfare prices. So first we'll understand about the algorithms used in first experiment. So the first one is ADA boost regression. ADA boost combines weak learners, usually decision trees, to create a strong model. It sequentially fits models to correct the errors of the previous ones. ADA boost is effective in handling complex relationships within data, making it suitable for capturing nuanced patterns in airfare pricing influenced by multiple factors. The second algorithm built is bagging regression. So bagging involves training multiple models independently and then combining their predictions. Random samples of the dataset are used to train each model. Bagging helps reduce overfitting and enhances model stability, potentially improving the robustness of airfare price predictions. The next algorithm built is gradient boosting regression. Gradient boosting builds an ensemble of weak learners, typically decision trees, sequentially. Each tree corrects errors made by the previous ones. Gradient boosting is powerful for capturing complex relationships and is often used in regression tasks to achieve high predictive accuracy. The next algorithm built is decision tree regression. So decision trees recursively split the data based on features, creating a tree structure. In regression, the average target value in leaf nodes is used for prediction. Decision trees are interpretable and can capture non-linear relationships in the data, making them suitable for understanding factors affecting airfare prices. The next one is random forest. So random forest builds multiple decision trees and combines their predictions. It introduces randomness during the tree building process, and random forest leverages the strengths of decision trees while addressing their tendency to overfit, making it suitable for robust airfare price predictions. The next one is extra tree. So extremely randomized trees or extra trees further randomize the tree building process compared to random forest, leading to increased diversity. Extra trees can enhance the robustness of the model by introducing additional randomness in the decision-making process. The next algorithm built is SVR, that is support vector regression. So SVR finds a hyperplane that best fits the data within a margin, aiming to minimize prediction errors while allowing for some tolerance. SVR is effective in capturing non-linear relationships and is suitable for scenarios where the relationship between features and airfare prices may be complex. The next algorithm built is MLP, that is multi-layer perceptron. So MLP is a type of artificial neural network with multiple layers of nodes. It is trained using backpropagation to learn complex patterns. MLP is versatile and can capture intricate relationships, making it suitable for predicting airfare prices influenced by numerous factors. The next one is VGG11, that is Visual Geometry Group 11. So VGG11 is a deep neural network architecture known for its simplicity. It consists of 11 layers, all of which are trainable, and it uses small 3x3 convolutional filters and max pooling layers to learn hierarchical features in the input data. The architecture is adapted for regression tasks by modifying the output layer. Instead of classifying discrete categories, the network is configured to predict continuous numerical values, making it suitable for predicting airfare prices. The next algorithm built is VGG13, that is Visual Geometry Group 13. So similar to VGG11, VGG13 is an extension with 13 trainable layers. The additional layers allow for the learning of more complex hierarchical features in the data. The next algorithm built is ResNet 18, that is Residual Network 18. So ResNet 18 is part of the ResNet architecture family, featuring a residual learning framework. It introduces skip connections, allowing the network to skip one or more layers during training, which helps in mitigating the vanishing gradient problem. ResNet 18 is adapted for regression by altering the output layer, transforming it into a regression model. The use of skip connections enables efficient learning of complex relationships in the data. The next algorithm used is ResNet 34, that is Residual Network 34. So ResNet 34 is a deeper variant of ResNet 18 consisting of 34 trainable layers. The increased depth allows the network to capture more intricate features in the data. The next one is MobileNet V1. So MobileNet V1 is designed for mobile and edge devices, emphasizing computational efficiency. It employs depth-wise separable convolutions to reduce the number of parameters and computations while maintaining expressive power. MobileNet V1 is adapted for regression by modifying the output layer. Its lightweight architecture makes it suitable for scenarios where computational resources may be constrained. And the next one is MobileNet V2. So MobileNet V2 is an improvement over MobileNet V1, introducing inverted residuals and linear bottlenecks. It enhances the efficiency of feature extraction while maintaining model accuracy. So now we'll understand about the algorithms used in second experiment. So we have used SVR and MLP in second experiment also. And the next algorithm used is QSVR, that is Quantum Support Vector Regression. So QSVR leverages quantum computing principles for support vector regression, introducing quantum entanglement and quantum gates to optimize the search for a hyperplane in regression tasks. The use of quantum states and operations enhance computational speed, making QSVR a promising avenue for regression problems. And the last algorithm built is QMLP, that is Quantum Multilayer Perceptron. So QMLP adapts the classical multilayer perceptron using quantum neurons and gates. With quantum entanglement and superposition, QMLP explores parallel processing and quantum data. Quantum gates and layers replace classical counterparts, showcasing the potential of quantum computing in the realm of artificial neural networks. Now we'll see the comparison graphs. So in the first experiment, the analysis focused on 4 major airlines, namely Aegean, Austrian, Lufthansa and Turkish, each featuring 6 different routes: Thessaloniki to Amsterdam, Thessaloniki to Stockholm, Thessaloniki to Brussels, Thessaloniki to Paris, Thessaloniki to Lisbon and Thessaloniki to Vienna. Across these airlines and routes, a total of 14 models were applied per route, encompassing diverse methodologies such as ADA boost, bagging, gradient boosting, decision tree, random forest, VGG11, VGG13, etc. So these are the horizontal bar graphs comparing R-square scores of the algorithms in the first experiment. The R-square value or coefficient of determination assesses how well machine learning and quantum models predict airfare prices. It ranges from 0 to 1, with 1 indicating perfect prediction. The R-square comparison graphs in the experiment show model performance across different airlines, routes and machine learning techniques, with higher R-square values signifying better predictive accuracy. And in the second experiment, concentrating on individual airlines such as Aegean, Austrian, Lufthansa and Turkish, the predictive performance of 4 models SVR, MLP, QSVR and QMLP was assessed. Each airline has its R-square comparison graph, providing a concise depiction of how effectively the chosen models predict airfare prices for each carrier. So these are the horizontal bar graphs comparing R-square scores of the algorithms in the second experiment. So the algorithm which is best performing in all the performance metrics will be used for predictions. So in these graphs, on x-axis I have R scores and on y-axis I have algorithm names. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is the dataset folder in which I have 2 main sections, first experiment and second experiment. Under first experiment, there are 4 folders for different airlines: Aegean, Austrian, Lufthansa and Turkish, and each airline folder contains data for 6 routes. This data is used for the first experiment, which involves testing various models to predict airfare prices for different airlines and routes. And in the second experiment section, there are again 4 files for the same 4 airlines, but the datasets here are specifically for evaluating models that predict airfare prices for individual airlines. And this is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And this is model file which contains algorithm information. This file will be loaded into the project code during runtime to utilize the trained models. And in first experiment folder and second experiment folder, I have associated Jupyter Notebook files. These Jupyter Notebook files contain a combination of code, graphs and outputs all in one place. Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. Now copy the path of the code folder from the address bar of the file explorer. I am copying it. And open Anaconda prompt. Use the command cd followed by a space and paste the copied path. And hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, the Flask framework will host the application locally at the default address, localhost and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to register. And if we already have an account, we can directly log in by clicking on the sign in link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password. And click on login button. So it has redirected us to the airfare price prediction page, and here we have to fill in these parameters. So first we'll understand these parameters. So the first one is departure time. It represents the time when the flight begins its journey. The next one is arrival time. So arrival time indicates the time when the flight is scheduled to reach its destination. This is day of the week. It is the specific day on which the flight operates. This is day before. It is the level of proximity to the departure day, indicating a day before. The next one is number of luggage. So it is the count of bags or items a passenger is carrying. The next one is number of stops. So it is the total count of immediate stops during the flight. This is overnight flight. So it indicates whether the flight includes overnight travel. And this is class. It is the chosen seating class or cabin category for the flight. Now we'll fill in these parameters. So click on this clock symbol. So here we have to select the departure time. I'm giving it as 16:10. And we have to select the arrival time. Click on the clock symbol. Arrival time would be 19:45. And day of the week would be Thursday. Day before would be 4. Number of luggage would be 1. Number of stops would be 1. Overnight flight would be no. And class would be 220. Now click on submit button. So here we can see the output, that is airfare price is $164.77 based on input data. Now we will try giving another set of parameters. Click on prediction link. So this time departure time would be 16:15. Arrival time would be 9:15. Day of the week would be Friday. Day before would be 12. Number of luggage would be 1. Number of stops would be 1. Overnight flight would be yes, and class would be 110. Now click on submit button. So here we can see the prediction. So airfare price predicted is $225.77 based on the given input data. We will try again. Click on prediction link. This time departure time would be 16:15 again. Arrival time would be 22:50. Day of the week would be Monday. Day before would be 15. Number of luggage is 1. Number of stops is 2. Overnight flight is no. And class would be 222. Now click on submit button. So here we can see the output. This time airfare price is $1,007 based on the given input. Now click on sign out link. Similarly, we can give any set of parameters and can get the predictions. So the conclusion here is The project systematically evaluated the predictive performance of various machine learning and quantum models in forecasting airfare prices. Through comprehensive analysis, the model's effectiveness was assessed across different airlines, routes, and specific parameters. And in the first experiment, involving multiple airlines and routes, the project provided valuable insights into the strengths and weaknesses of diverse machine learning models. The R-square comparison graphs offered a nuanced understanding of each model's predictive capabilities under varied conditions. The second experiment concentrated exclusively on individual airlines, employing 4 distinct models. The project explored how well support vector regression, multi-layer perceptron, quantum support vector regression, and quantum multi-layer perceptron performed in predicting airfare prices for specific carriers. Parameters such as departure time, arrival time, day of the week, day before proximity, etc. were found to significantly impact the accuracy of airfare predictions. Understanding these influences is crucial for refining models and enhancing prediction accuracy. And the findings from this project hold practical implementations for the aviation industry and travel planning. Future work could focus on refining models, incorporating more advanced quantum computing techniques, and expanding the dataset to further improve the accuracy and applicability of airfare prediction models in real-world scenarios.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.